Hi, everyone. Welcome to the Infrastructure Network. My name is Chad Smeltzer. I am your host. Today's guest is George Kurz, who has been active in sanitary sewer studies, evaluations, hydraulic modeling, I&I, inspection, anything you can think of when it comes to sewer systems. George has been involved in. He started back in 1974 after he graduated from Tennessee Tech University. So today we are going to talk about the good, the bad, the kind of ugly of sewer systems and why we haven't found I&I, why we haven't fixed these things in sewer systems, and where does it all start and where does it all end. So George gives us his opinions and ideas of what he thinks and how we can move forward in the future. So we hope you enjoy the content. Thank you so much for following us and listening to our content. We hope you enjoy it. Have a great day. Today we have a special guest, George Kurz, who is the licensed professional engineer and consultant for his own firm. Thanks for joining me, George.
Thank you, Chad. It's a pleasure to be here, and also certainly interesting from our previous conversations about sewer systems and I&I.
And that's a great way to lead into this. Going into your history and where you all started as an environmental engineer, professional engineer, you're specialized in sewer systems, right? And how did that start? Where did you get your, licensing and engineering degree and stuff like that?
Okay. I actually graduated from Tennessee Tech University in Cookeville, Tennessee in 1974, and then went on and did some graduate work. I didn't get a further degree from that, but that's what it took to really make me feel comfortable of going out into the profession. And I really kind of evolved into environmental engineering during the time I was in college. And I had originally, my childhood dream was to work on dams. That was the real great pleasure of my life, and to think about working on dams. And when my family moved to Tennessee, or East Tennessee, with Tennessee Valley Authority and all the big dams on the Tennessee River, I thought this is heaven. I have arrived. But over the years, I began to, while I was in college, began to have somewhat of a different view. I still love to go explore through a dam, or I enjoy seeing how they're built and what have you. But I realized I was more interested in the system of dams, of how they work together. And then that started me thinking in terms of the environment, of how all different components of our world around us and our created world work together to either enhance or sometimes degrade the environment, unfortunately. And so I've always had a long-term interest in water, no matter how it's used or where it occurs. So over time, I shifted more into what used to be called sanitary engineering. Now it's environmental engineering, but always a large component of that are the hydraulics of flow. Yeah. And there's plenty of hydraulic issues in treatment plants, and particularly out in the piping system of sewage collection systems.
Yeah.
So my first job was 1976 with the Division of Water Quality Control with the state of Tennessee. And at that time, I was reviewing plans and specifications for treatment plants, for industrial waste facilities, sewage collection systems. All the plans and specs had to be sent in from municipalities that were planning on expanding their systems. And I began to focus more on what was then called pretreatment programs. It was the pretreatment of industrial waste that were going into sanitary sewer systems and had to be treated at municipal facilities. And that led to a change of jobs. I went to work for City of Chattanooga to create and set up the first pretreatment program in Tennessee, and one of the first in the country. And it was the first one fully authorized and approved by EPA in Tennessee, and again also it was also the first ones that or only ones that was approved on time by the federal schedule. That was a point of pride. But anyway, once we got that running pretty well, I began seeing more and more problems that were out in the sewer system and that have been addressed in a kind of halfway manner over the years. But by 1985, EPA came up with they had been observing nationwide problems, and some of them were pretreatment, some were plant operations or plants that weren't working right. There were lots of sewer overflows, many different kinds of problems. So they had been up to that time working more on a basis of a kind of focused program approaches. And it seemed like it kind of threw up their hands at finally and said, okay, we're going to go at this and do it with a questionnaire nationwide to everybody that has a plant. And you're going to tell us what the problem is, and then we're going to write an order to tell you to fix
Oh,
it.
okay. Wow.
And this was called the National Municipal Compliance Policy in
Okay.
1985. So they dumped it down to the states. The states dumped it down to my boss in Chattanooga. My boss dropped it on my desk. And it was about a 25-page questionnaire, right? Try to figure out what's wrong with your system. And I remember reading through it and thinking, well, we can work on this and we're okay here. And then when I went back to the beginning and started to fill it out and document, and I thought, oh my gosh, we are in trouble. We are not doing a lot of the stuff that's expected here. And my point is that when I had to actually put pen to paper and say, what are you actually doing?
Yeah.
What I had breezed over in my mind but then had to actually document it. That was where the difference was. And it was kind of a personal, watershed for me to come to that realization. And one of the big things that we had as problems, we were doing very well on pretreatment, but we were doing very poorly on sewer overflows. And so that was really the beginning of it. And I had to be educated in it. I mean, this was 1985, so I had left school 11 years before. And I really had not been trained in overflows. I was aware they happened, but I'm sorry to say, and embarrassed to say a little bit, that it just wasn't high on my radar list. And
Yeah.
So then it became that way, and I began studying them. I studied our system, documenting where they were located, and trying to work out the causes. And shortly thereafter, because I'd already knew flow monitoring pretty well, because we had to do flow monitoring for the industries coming into our system, we began setting up networks of flow meters and rain gauges out in our system and began really studying what was going on out there and seeing the variation that was due to seasonal groundwater levels and seasonal rainfall. Excuse me. So that was really the beginning of focusing, and it came in a timely fashion in that flow monitoring technology had evolved very quickly. And by 1987, when we began deploying these systems, we had very good area velocity meters that still are in existence today that operate very efficiently. There's been some improvements, certainly, in the past 30 years. But the basic concepts behind it was a huge breakthrough to allow us to be able to really study sewer system. So that was the beginning of it. And then in 1990, I went to work for a private company that was handling the sewer system overflow abatement program in Nashville.
Okay.
And so I brought my expertise of the flow monitoring and the analysis, the analytical techniques. And that really was the big breakthrough for me, because I had ultimately, we handled about 700 temporary meters. There were like 50 permanent meters out in the Nashville system. The Nashville system had about 2,000 miles of sewer.
That's a lot.
Well, so part of that was a combined sewer as well. And we had to have a way to analyze it. Just having a hydrograph, which anybody, my grandkids could do that, draw a graph of the daily flow. But there's a person that I consider as a mentor, who's Pat Stevens. He had a phrase for talking about human speed analysis and human speed data, that you just having a graph with a lot of chop all over it, the human mind has a hard time grasping that. Whereas if there is a way to boil that down into meaningful intelligence, then people could use that to begin making decisions about what's going on. Say, well, this system's worse than that system. You can compare the two rather than these two choppy lines and say, I mean, quite frankly, I can't do it. And I've been looking at this stuff for over 4 decades. So that was what I worked on, and I so we began doing the analysis. The other thing was that when I was hired there, one of the first things my boss asked me to do, he said, "I want you to work out some kind of numerical criteria by which we could determine or making the decision whether we line this line or do a patch on it or what when we're going out to do rehabilitation." So I started doing that. And this was all kind of going on simultaneously. It was kind of like having hit the ground running or repairing the machine while you're flying type thing. And so I came up with a system, and quite frankly, other people have done this. When I was doing the research, I had access to. There was probably at least 6 or 7 other systems, and probably many more other than that, but ones that have been published. So I used some of that, tried to tailor it to what we needed. Well, after a while, when I was, we'd be handed a project, we'd be looking at it to evaluate it, and I'd run it through this little numerical thing and say, okay, this gets so many points and that's so many. After a while, I began to realize that I could throw it away. It was really simple. That the decision factors that came in, and part of this was, keep in mind that while we were doing this, I was also evaluating flow monitoring before and after from projects that we had done. And when I began to see more and more that our projects were where we got good effectiveness was just going out and lining. Now, I don't advocate lining everything by a long shot, but what it turned out to be was that if we had 3 or more, keep in mind we were using paper records at this time with the TV records.
Right.
This was early 90s. I mean, there were computers out there, but not really well set up unless you created stuff yourself. If a paper record indicates there are 3 or more major defects on a line segment, typically 250 to 300 feet, line it. In other words, all the counting of how many little cracks do we have, and the assessment type thing. And I'm all for doing assessment. I'm not against that, but it turned out that it really didn't have to get down to 3 decimal points accuracy to figure out whether or not you line it or not. Now, sometimes there were intermediate cases, and what we found, what was more relevant at that time, and I still feel like this is the case, is it adjacent to lines that were already deteriorating? In other words, what I began to realize, these lines were all, if they were built about the same time with the same crews, with the same materials, in the same creek beds, which is a lot of what stuff gets laid in, or at least swales where drainage. So you're going to have a concentration of water there. That a line that didn't happen to have failed yet was probably close to failure if it was in that same project. And it was just a matter, it just hadn't gotten to that point yet. So it was worth going ahead and lining it and taking care of, doing the rehabilitation and take care of it. Another thing that we kind of came up with, some people have different phrases for it. I called it the system approach. In other words, looking at the pipes, the manholes, and the laterals all together. That if we had, and there's some history behind this, there was a big company, one of the major companies in the industry, that had developed a lining technique for or cured in place lining technique for lining service laterals connected to lines that already had been lined. And they were experimenting with this, and Nashville was one of the first areas that did experimenting with this and did very detailed before and after flow monitoring to be able to see what were the results. And the results that we got were showed that it was absolutely essential to do the laterals at the same, either as part of the same project or do it at the same time when you're out there doing the pipe.
Right.
So at least it doesn't all have to be done exactly simultaneously, but at least it's part of the same project. If you're going to treat a project area and you pick the line to line, then you need to do the laterals and the adjacent or contiguous manholes as well. Because what happens is, and I boil this down to one of my rules, is one of the major goals of the sewer rehabilitation project is to stop migration of water.
That's the goal, right?
Stop migration of water. That people have known how to seal lines very well for years, but and this was something that was actually fostered by EPA, unfortunately. They back when I was at the state, they had a procedure for what was going to be allowed under an EPA project to be paid for. This was back in the good old days when the EPA paid like up to 75% of projects. That was a nice chunk of money. Well, they were very strict of saying we're only going to pay for things that are cost effective. And honest to gosh, this is how it worked. They had computers then too. It was 70s and 80s. But what they did is all the stuff, information that was gathered was put on cards, computer cards.
Yeah.
If you ever remember those. And they would run them through a card sorter, and then it would print out some, and we get these big books, lists of sewer lines with defects. And they list them in order of the amount of water that was observed or leakage observed by the operator. And only the ones that were above a certain line of cost effectiveness were allowed to be fixed. Now, the trouble is the next defect below that cutoff line could be right next to one of the largest leaks in the system. But only that big leak was allowed to be fixed. The other leak was not. Guess what's going to happen to the water when you seal it of one big crack and then two joints down the pipeline? You got this other crack. It's just going to migrate.
Right.
It's intuitive, but this is part of the problem. And now here I'm only guessing, but I feel that part of that program from EPA years ago was developed by accountants. And, I don't want to do accounting, but I don't think some of them should do engineering. So,
right.
Anyway, when we began to take into account some of these common sense things, that's when we began really seeing good results from our sewer rehabilitation program. And when I say good results, we had set up just almost initially as a goal 50% reduction. And we actually were achieving this on an aggregate basis. There were some projects that didn't get quite 50%, but there's some that got 70%. So on an aggregate for all the work we were doing up to that time, and I'm talking about 90 some miles of lining, we had gotten over 50% or more of the annual INI and also 50% of the peak RDII, which is what we're going to focus on, or what is likely to cause your overflow. So we were getting a good rate of success for overflow reduction. And we were also measuring overflows too, by the way.
Right.
The one thing I felt like that was missing in really the regulatory folks and the engineering thinking too is we would get so much money to do a project, we design the project, we install it, we'd have an inspector to say, come back and say, okay, the project's in, we're fine, let's go on to the next project. No. We've got to monitor it to see the goal of the project was not to line the pipe.
Right.
The goal of the project was to reduce the leakage. And if you haven't reduced the leakage, the project's not done.
Right.
And that's a key byword in my mind to make sure of what we're trying to achieve.
So, with all your experience and all that and you talked about 1985 when CMOM was kind of implemented and developed by the EPA. Is that
No,
kind of the same time?
Now, CMOM came a bit later, and I knew the guy that was the father of CMOM, by the way. He died a couple years ago, and he was the chief of enforcement down in Region 4, and he came up with what we called the MOM program.
Yeah.
And then when he griped to me a lot of times. He said, well, when headquarters got a hold of it, they added on CMOM. Now, I get it why he might gripe, because he was.
Yeah.
But I like the idea. He said, well, it's inherent in there. Well, inherent to guys like him and to me, but maybe it's not obvious to other people. So it was good to add on the C part, the capacity part. CMOM really came in more in the late 80. Well, I'd say in the 90s. That was more what he was doing. And he made the point about CMOM that actually all the elements of CMOM were already in the law and in the regulations. And what he was trying to do when he pulled it all together was just that, pull it together so that a municipal agency could see it in one package, in one place, and not have to be hunting all over the Federal Register to find it.
Right.
But that was his specialty, and what he made a huge contribution then to other people like Steve Albee.
So with all your experience, George, and all the knowledge you had and the successes you had reducing I&I, down in Tennessee and Nashville area, why don't you think more of what you've done, the success-wise, hasn't been replicated throughout the country? Because I still hear the stories of flow monitoring is still existence. Nothing's really changed. There's a lot of I&I, and the problem's still not being addressed. Do you have any insight on why that might be?
Somewhat, but I will cite it more as I want to be clear that in some cases it can only be my opinion. That's an educated opinion, or at least experiential opinion, but it is opinion. It's not something I can particularly prove.
Right.
And that is that let's first look at what a lot of the drivers, or really the main driver for sewer rehabilitation, it ought to, even this is a contradiction. To me, it ought to be a common sense thing that in a community, you don't want leaking sewers. That ought to be the driver.
Right.
But unfortunately, in our business, a lot of it is out of sight, out of mind. Somebody may see an overflow out in the woods, but unless it's right in front of their house, most of the time it's not on their top of their radar system. So that means that really the driver for a lot of sewer rehabilitation programs and correction of overflows is from the regulatory agencies. So starting with EPA, working its way down to the states. So they're interested in stopping overflows. And that's a good thing. I want to stop overflows.
Yeah. Nobody wants sewage in their basement.
That's it. Motherhood apple pie. So the trouble is, and I have gotten this anecdotally from individuals talking about their contact with the state, and even state people talking about their contacts with EPA, that I've been told the EPA really doesn't care a lot about I&I. I guess intellectually they recognize that I&I causes or is one of the main causes of overflows, but they're really taking a head in the sand type of approach of saying we'll regulate you if you have overflows. Then we're going to take enforcement action on you, and then it's your problem. You figure it out how to take care of it.
Right.
The trouble is with sewer systems and overflows, it's kind of like human beings and heart attacks. People, one of the things that can lead to heart attack, I'm not trying to be a doctor here, but I know for myself, I've got high cholesterol. Okay, I have to be careful about that. Cholesterol clogs up the arteries, clogs up the piping system. And so you have these problems in the piping system that build up over the years, and it causes more and more surcharging. It causes more and more backups. It's decreasing the carriage capacity of the system. Excess I&I decreases the carriage capacity of the system for the normal flow. And then all of a sudden, one day, you get a trigger and you have an overflow. You have a heart attack.
Right.
It's not a perfect analogy. I apologize for that, but I
No,
think
it makes sense. Yeah, it's the easiest way to understand it.
And the reason why I use that analogy is that you have the problem building up over a long period of time. Now, modern medicine, thank goodness, has ways to detect the problem in its early stages. And I maintain that in our business, we've got the means to detect these problems early on and predict where they're heading. And that's exactly what I do with my system of regression analysis, which is even recognized by WRF. Not my system per se, but the idea of using regression approaches is recognized by WRF, the Water Environment Research Foundation, as being one of the more accurate ways to analyze this. Mm-hmm. That this can be a tool that communities and engineers can see where their system is heading and ring the alarm bell and say, it's time to get out there. We got to find out, what we can do about it. And flow monitoring is it. Another analogy I make is that flow monitoring on a permanent basis, not just bring them in temporarily, but you really have to keep a finger on the pulse of what's going on in the system. It's kind of like the old dew line. I don't know if you remember that. Yeah. I guess because I'm a cold dinosaur from the Cold War era. The dew line was a distant early warning radar system up in Alaska and Canada that detect if missiles were coming over the North Pole. And you detect the problem early on so you can do something about it. That's the point. And the point of flow monitoring is that's your tool to detect it.
So if you think flow monitoring has been around a long time, and I've been in that world working with other engineering firms that have a lot of flow data and flow monitors, it's expensive to put in flow monitors and throughout the system. It's very time consuming and expensive to put them in. But once they're in, like you said, it's a great tool to collect information, collect data levels, right? I mean, that's what we're looking for.
That's right. And I agree that it's expensive. I wouldn't want to take it out of my paycheck next week. But the thing is, when you do a hierarchy of the expense of sewer rehabilitation, now you're talking real money. And the thing is that the flow monitoring is kind of like the steering gear to say, go here or go there. And there have been projects that actually have been conducted. One was up in Indianapolis, I think back in the 70s. And in fact, Pat Stevens was the guy that was the director up there at that time and put this project together to determine essentially what is the optimum number of flow meters that you need out there so that you can properly subdivide a system and say, here's where your problem is. And when he did that, I know this is going to sound like an old wives' tale, but it actually works out of the old rule of thumb of roughly 80% of the problem is, in fact, in 20% of the system. Now, it might be 81 and 19%. I'm saying in a rough proportion, that's what it works out to be. And I can give you an easy example to think about. Okay, I've studied all 243 municipal agencies in Tennessee. And I've analyzed a year's worth of data to figure out how much I&I they have on an annual basis and on a peak basis. So let's take the worst system that I saw. And we know you can say, well, this is the worst system. Now, what do? you say, well, it's the worst system. It's so bad. Go out and line everything. It really doesn't make sense because there's probably something out there you don't need to line.
Right.
So then you could say, okay, well, because if using the data I had was only at the meter at the treatment plant, so there's only one meter for the whole city. So they say, well, I want to save money. I'll put in one more meter. So we'll divide the system in half. And God only knows, surely one half will be worse than the other. So does that mean, well, we only treat the half that you subdivided? Well, that's where we'll do the work. We'll line everything in that system. We'll take care of the problem. Well, intuitively, that's probably not the best way to do it. So maybe we ought to put out 3, 4, 10. And there's a roughly Pat worked out a rule of thumb that if you have a meter about every 10,000 feet, now that would be more, in my opinion, more on the temporary metering. And do that, then you can subdivide your system sufficiently to say, okay, area A, C, and F, they're the hot spots, knock them out.
Yeah.
And another advantage of doing it that way is you can set up a small enough basin. I call it an area a basin,
right?
An old tradition. That you can use that as a pilot, particularly in a town where they've never done anything like this. Is no, does that stuff really work? Well, try it on a small basin you know is really bad, and do the before and after monitoring. And what that does is then that helps build confidence for that community and the community leaders to say, wow, I guess it really does work. It's worth continuing on to do this. So, and also another thing is it keeps the cost down because these things need to be multi-year projects. You can't do it all in one year.
Right.
So there's numerous benefits by doing it that way.
There's a new bunch of technology coming out now, kind of going, and we only got a couple more minutes left for the podcast, but new technology is coming out now as far as ultrasonic level meters. They've been used over the last 10 years or so, but now they're becoming cheaper and faster to deploy in collection systems. Mm-hmm. Where do you see the difference between area velocity meters needing the velocity versus level meters? Is there a difference?
Yeah. Now, there's a wide variety out there. Now, to be a little more precise, area velocity meters had to have ultrasonic depth instruments in them. That's
over like 2 inches, right? I mean, because it had to get over the Doppler sensor, mostly like 2 inches or so. It had to get over
Doppler is reading an ultrasonic signal.
Yeah, got it. Okay.
It's an ultrasonic signal no matter what, and you're reading the Doppler return is it's kind of run together there. But now there's for some shallow ones, and even one of the best meters that I've seen out there, they're going back as a backup. They're having depth sensing using pressure sensors, and that's the main thing is you get a good reliable depth, and the depth has a greater effect on the accuracy of your final reading in some ways more than the velocity does. Now, velocity is very tricky because you cannot read with an instrument the average velocity.
Okay.
One single instrument will not do it. You're actually reading a point. And then different companies have different algorithms for converting that point, depending on where they're reading it. If they're reading it up in the max, one company, for example, their procedure was to read the highest velocity particle in the stream. And then they could back that off by using a factor of 90%, and then come up with an average on that. But that depends on having uniform flow,
all kinds of things. Yeah.
Yeah, it's some good flow characteristics. But the European Union, for example, years ago anyway, they felt like that you could not have an ultrasonic sensor be better than within a 10% accuracy range. So
Mm.
if somebody gives you an exact number, that's good and you work with it, but there should always be in the back of your mind plus or minus 10%. Now,
Okay.
this is one reason why I am a proponent of using a statistical method, because it kind of gives you a little cushion to allow for that kind of variability.
Yeah. And there's a bunch of different people that say different things about ultrasonic, with the depth, right? In the old days, people would say they would pop manholes, right? And that's how you knew when a raining event was occurring. You go out and pop manholes. You'll know where a lot of the I&I was coming from. I mean, you could just see the level higher, especially if there's only 20 houses
Right,
connected to an 8-inch or 6-inch sewer. You knew downstream if it was running 5 inches or 6 inches, there was a problem, right? I mean,
right.
that's really kind of how you used to look at it. But I guess what I'm getting at now, people are saying that Manning's equation just doesn't add up anymore the way we thought it was going to be, and this ultrasonic level meters are now becoming a quicker way to assess areas of I&I, because you can just look at the levels going up and down. Just
I
curious.
think, excuse me a second, I think what you're
Sure.
talking about is actually an overall philosophy called, or that I've been trained called micro monitoring.
Okay.
I'm sorry, I should have picked up on that earlier. The
And I didn't use the right term. Sorry. So,
No problem, no problem. The idea of micro monitoring is you deploy a SCAD of very inexpensive uh, level detection instruments only.
right.
You're not getting area velocity. Now, I can assure you, area velocity is the best way to get true volume. If you want
Okay.
to do before and after, and particularly if you're paying for it, or you're partly going to get paid as far as the success of your project, you have to do it by area velocity. But now, micro monitoring would be more in the category of you deploy that early on in a project, and it helps you narrow down to your really bad areas.
Right.
Or another way to use it is once you have defined a really bad area of a big basin with more traditional flow monitoring instruments, then you can deploy the micro monitors out there, and it'll save a lot of time. You'll get a very quick reading right after one or maybe two storms and say, it's these segments 6, 5, and 3.
Yeah.
Those are the ones to do. So there is value in both. And it's kind
Okay.
of like, think about a toolbox.
Yeah.
And you've got a bunch of different tools in the toolbox. And I like to think about that that's one of the functions and responsibilities of the engineer, is to select the right tool or the best tool for the particular application,
Yeah.
rather than, uh, you know, each flow monitoring company, they're fine. And I use a lot of them, or have used a lot of them over the years.
Yeah.
But you can run into a situation of the old deal of, to a hammer, every problem is a nail.
Yeah. That's a good analogy. so,
So,
so go ahead.
that's all right. I was just thinking about in that regard, then the engineer becomes somewhat of the gatekeeper on it. But, it has to be an experienced person that's
Yeah.
familiar with those different technologies.
Yeah. I just did a podcast episode or an event where we talked about I&I, because there's an engineer out of Canada, Barbara Robinson. She talks about, first of all, the installation of contractors, when you design a development, for example, and the contractors go in and put all the underground infrastructure in, she's seeing a huge problem with the way they're putting in the pipes. First of all, that they're already leaking even at an early stage of the development. I mean, they're just not doing quality, and we're missing out on inspecting or holding people accountable there. And then it just kind of escalates over the decades as time goes on. You get more and more I&I getting in those spots. So it kind of starts at the beginning, and then you deal with all the repercussions later if you don't have a good accountability system in your I guess infrastructure development. So
You're
just
exactly right. And I've observed at times that some municipal agencies, to save money,
Yeah.
Say, well, we don't want to hire an inspector. We'll do our own inspection.
Yeah.
And it's not that some of the people aren't good inspectors, but there's trouble is when they're working for the agency. And I've seen this, and I worked for Chattanooga for 12 and a half years. I saw
Yeah.
things like not so much, I won't say specifically that kind of problem, but I had enough problems out in the treatment plant agency. If we said, well, we'll assign somebody else from that's already on staff to do that job part time. Well, guess what? It doesn't work.
No.
Generally, it doesn't work very well. You get an overworked person, number one. And then secondly, their primary duty, they know what it is and they know which side of the bread their butter's on, and they're going to take care of that. And they should.
Yeah.
It's kind of a crazy situation to try to save money and squeeze people.
Yeah.
And it doesn't pay in the long run. And I would definitely agree that there's systems or pipelines being put in there by developers where it's not properly inspected, wasn't put in the standards, and you have to have some body and some agency with enough punch to say, "Hey, we're not accepting it, and you're going to dig it up."
And that's it right there. That's one thing I've learned a lot is agencies do not want to deal with the lawsuits or legal issues of trying to hold a contractor liable for the issue. So they just kind of put it under the rug. They're like, yeah, it's good for now, whatever. Somebody else will deal with it 50 years from now, that kind of mindset. It's like, that's not good. If you're not holding them accountable, they keep going to the next city doing the same thing. And then
Mm-hmm.
we end up with the same problems everywhere. So if you really think of it that way.
That's exactly right. And I have had the good fortune to work with some really fine contractors.
And there is, yeah.
Contractors that taught me. So
Yeah.
I'm not going to sit here and say engineers are God by any stretch of the imagination.
Right.
But sadly, there are ones out there that don't do a good job, and sometimes it's not trying to be crooks. They're ignorant, but
Right.
then that's how they have to learn. If you rip out a few pipes, after a while, you learn how to do it right.
Right. What do you think the future is of I&I? Because it's still a massive problem. We spend billions of dollars on it, and we still can't solve the problem.
I would contend that actually we haven't spent enough, and that because we have not really focused on the problem. There's lots of money out there that has been spent to stop overflows. Okay?
Yeah.
Now, you may be thinking, well, wait a minute, didn't I just say that? No, I'm splitting hairs on you. There's a movement that has been going on for decades here to say, we'll build a tank.
Yeah.
Well, I'll give you an example. When I was doing this research on Tennessee, of all the systems in Tennessee, I came to this little town called Bell Buckle, down kind of south of Nashville. I couldn't tell you out of the population size or whatever, but I know that they were actually studied by EPA in 1981 as part of what was then called the Conklin study. If anybody wants to historically look it up. And they had a terrible problem with online, and that didn't go away. And sometime after that, somebody got the brilliant idea to build a tank. Well, how I found out about it was when I was doing my research, and I got a hold of a year's worth of data in 2012 for this town, and I also got a record of all the overflows they had. And there was a record of an overflow at that tank.
Wow.
The point being, R&I does not get better. So now that little town, which probably strained its butt to build, have enough money to build that tank, they're not only stuck with the tank, they're stuck with the maintenance on the tank, the O&M of the tank on top of the O&M of the plant and everything else. Yeah. And they still got the problem.
That's an interesting.
That infuriates me. I'm a citizen like everybody else. I pay sewer fees, and I'm glad to pay it. I'm glad to have somebody take the sewage away so it doesn't stack up in my backyard. But
and before we end here, I just want to you made up a great point, because I just kind of ran into this morning where, engineering firms can be the gatekeepers, influencers of these little municipalities. And then if you get the wrong influencer or the wrong gatekeeper telling you need to do certain things and they don't have the right education, by example, the tank being put in place, you spend all that money and it didn't really work out the way it was supposed to. Like the poor city is there vulnerable. Like it's just stuck now. They just didn't have the resources to do better, due diligence of figuring out what their, solution could have been, but they went with the wrong one. And, that's examples of like how gatekeepers, influencers can really change the way we look at things in our cities and communities.
It is. And uh, before I have people send bombs to my mailbox, there may well be times to use a tank. If you're in a crisis situation and you've got to get something done fast, that might be an answer. As I said earlier, it is one potential solution that's in the toolbox.
Right.
But in my opinion, it's been overused as being for one thing, is because cities have been delayed so much, and then they get under these orders. And the trouble is, the EPA is not looking for the long-term solution. They said, you fix this overflow. And city says, well, the only way I can do it is by building a tank. And so he says, fine, fix the overflow. So,
Yeah, that's a good point. Yeah. So then the EPA is fine with it, but it didn't really solve the problem
that's
completely. Yeah. That's interesting. Well, George, it's been amazing talking to you and listening to all your history and your experience and understanding more about you and hearing the stories have been great. How can people get a hold of you? I know we don't want people bombing you with emails. You won't get that. Don't worry. But how can people get a hold of you if they want to learn more?
It's my email is out there, and it's george.kurz@comcast.com. I get plenty of spam mail anyway, so if you want to add a little more, that'd be fine.
Yeah.
And I'll evaluate it. I'm on LinkedIn, and
Sounds good.
I'm glad to talk to people about I&I and I&I reduction. I'd like to see some genuine progress be made on this before they put me under the ground.
I think we're going to have you back for another episode, maybe with some other I&I experts and going back and forth and learning from, how you guys, communicate together and what different opinions you guys have, because that's important to look at things objectively and come up with better, solutions, maybe. Who knows? But we'll keep you in the loop.
Great. Well, really thank you for this opportunity, Chad.